In this video, we're going to analyze the graphs of functions, and we're going to find some characteristics of those graphs. For example, we're going to look at how to find domain range. We're going to find the intercepts, x and y intercepts, intervals increasing, decreasing, and constant, as well as symmetry. So test for symmetry. If we are trying to figure out whether or not a graph is symmetric with the x-axis, the y-axis, or the origin, what can we do to test for those symmetries? Well, it all has to do with substituting the negative in, the opposite. So if we substitute negative x for x and the result is the same equation over, then we're going to have symmetry with y. Symmetric with respect to the x-axis, we can substitute a negative in for y, and then we result in the same equivalent equation. Then we have respect with the x-axis. Symmetric with respect to the origin is going to be substituting negative x in for x and negative y in for y, and see if you get an equivalent equation. So let's do some examples. So let's say I'm going to test for all three symmetries. So I'm going to start with symmetry with the y-axis. That means I'm going to plug in negative x. So plugging in negative x means I'm going to do y equals negative x cubed. Well, when I simplify y equals negative x cubed, then that's going to give me y equals negative x to the third power. Because this is negative x times negative x times negative x. It's negative x to the third. Well, that is not exactly the same as y to the x to the third power. So we do not have symmetry with the y-axis. So no symmetry with the y. So what about symmetry with the x-axis? Well, that means I'm going to plug in negative y into my formula, and then I'll simplify. Well, to simplify, we would divide by negative 1. So y equals negative x to the third. And again, those are not the same equation, so we do not have symmetry with the x-axis. So the last one we're going to check is symmetry with the origin, which means we're going to plug in a negative y and a negative x and see what results. Well, negative y equals negative x to the third power. That would result in negative y equals negative x to the third power, because again, negative x cubed is negative x to the third power. Divide that by negative 1, and our result is y equals x to the third power. Well, that is the same as my original. So therefore, this has symmetry with the origin. Okay? So let's try another one. So when we plug in y equals, plug in negative x squared plus 5, and we simplify that, we get y equals negative x squared is x squared plus 5, which is the exact same thing. So therefore, this has symmetry with the y-axis. Let's check it for the x-axis. So we're going to plug in negative y equals x squared plus 5. And again, you divide by negative 1, you'd get negative x squared minus 5. So that does not have symmetry with the x-axis. And then to plug in both, negative y equals negative x squared plus 5. Well, that's going to give me negative y equals x squared plus 5. And again, divide by negative 1, you get y equals negative x squared minus 5. So that also does not have symmetry. So the only symmetry we have with y equals x squared plus 5 is symmetry with the y-axis. Okay, let's test number 3. We're going to plug in negative x squared plus y plus 1 squared equals 4. And then when we simplify, that gives me x squared plus y plus 1 squared equals 4, which is the same as the beginning. So we do have symmetry with the y-axis. Let's check the others. So x squared plus negative y plus 1 squared equals 4. Well, I can't simplify that to get the exact same thing out. So we're not going to have symmetry with the x-axis. And a very similar thing is going to happen when we make both of them negative is I can't simplify that out. So because of the negative y plus 1 squared, it's also not going to be symmetric to the origin. All right, let's try this last one. Y equals negative, the absolute value of negative x minus 2. Well, remember, the absolute value of negative x, whatever it is going to be a positive. It's going to be the same thing as the absolute value of x. So therefore, we have symmetry with the y-axis. Okay, when we do negative y equals the absolute value of x minus 2, I divide by negative 1. Y equals negative the absolute value of x plus 2. That is not the same thing, so there's no symmetry with the x-axis. And then when I change both, negative y equals the absolute value of negative x plus 2. When I change both, I get the negative y equals that's absolute value of x plus 2, because those are the same thing. Then I divide by the negative 1, so that's going to give me negative absolute value of x minus 2. So again, there's no symmetry with the origin on that one either. So another aspect of symmetry is identifying whether a graph is even or odd. A graph is even if it has symmetry with the y-axis. In other words, when we plug in negative x, the result is exactly the same function. An odd function has symmetry with the origin. Now, in our symmetry video, we talked about changing x and y. Here, we have a simpler test to use, and that is on a function, if we plug in negative x, and the result is a function that is exactly opposite of my original function, then we have symmetry with respect to the origin. And so that applies, kind of adds on to what we looked at when we did symmetry. So let's look at some examples of this. So let's look at this first one. If I plug negative x in, I'm going to get negative x to the 4th power minus negative x to the 2nd power plus 2. Well, negative x to the 4th power, that means multiplying negative x times negative x times negative x times negative x. That's going to give me, because there's 4 negatives, positive x to the 4th. And then negative x squared is going to give me a positive x squared. So this is going to result in minus x squared. And then this doesn't multiply by anything, so it's going to be plus 2. Now, look at your original function and look at your new function. They are exactly the same, so therefore these functions are, this function is even. All right, let's do another one. So f of negative x equals negative x cubed minus negative x plus 3. Well, again, negative x cubed is going to result in negative x to the 3rd power, because there's 3 negatives. That's going to leave it negative. Then it's going to be to the 3rd power. And then minus a negative here creates a plus x. And then I don't have anything to multiply there, so plus 3. Now compare that to the original. This is x cubed, negative x cubed, so that's opposite. This is negative x, positive x, that's opposite. But look at this last term. Look at the very last term. It's plus 3 plus 3. What that means is these are not exact opposites. They're also not exactly the same, so this would be a neither situation. This is neither even nor odd. Not all functions have symmetry, so neither is an option. So let's look at another one. F of negative x is going to be negative x cubed minus negative x. Well, negative x cubed is negative x to the 3rd power. Minus a negative is plus. And when I compare to my original function up here of x cubed minus x, negative x cubed plus x is the exact opposite. They're exactly opposite. You can see that because x cubed here is positive, here it's negative. X here is negative, here it's positive. So they're exactly the opposite. So opposite means that they are odd functions. Graphically, we can just look at them and say, are they symmetric to the y-axis or the origin? In this case, when I draw the line of symmetry there, I can see that this side of the graph is mirrored on this side. So it has to have symmetry with the y for that to happen. So this would be an example of an even function on a graph. Now, an odd function is a little bit harder because you've got symmetry with a point, the origin. So it's flipped over the origin. So this part of the graph is flipped over. Kind of think of it as being flipped over x and y simultaneously, but you notice you get that same shape when you rotate it around. And so this would be considered an odd function.